Hey, grade sevens. So today we are actually going to be going through the rest of chapter 5 on probability, 3 sections on it. Don't worry, it's not actually too crazy how much information there is. You sort of already know most of it. Um, just because we've actually been asked to be done all our new teaching before that last week of school. So we have less than 3 weeks left now. So I'm going to get into it. So we're just looking at probabilities of simple independent events. We've already been making tree diagrams and tables to find all the sample space. So that's all the possible outcomes. So now we're just going to be using that to actually find the probabilities. So let's use a tree diagram in this case. So it says a school gym has 3 doors on the stage and 2 back doors. So a total of 5 doors. You can see from the picture, 1, 2, 3, 4, 5. Make my line a little bit skinnier. So during the play, each character enters through one of the 5 doors. They can enter through any one of the 5 doors. And then the next character can be either a boy or girl. So it says draw a tree diagram to show the sample space. So it's the sample space is saying what are the possible outcomes of what door a character goes through and whether the next character is a boy or a girl. So before that first person goes through, there's 5 options that they have. And we'll just number them 1, 2, 3, 4, 5. So they can come out of the first door, the second door, the third door, the fourth door, or the 5th door, right? They can come out one of those. Now, whatever one they come through, doesn't matter which one they come through, which makes these independent events because one doesn't affect the other. No matter which one they come through, the next character to enter can either be a boy or a girl. So if they come in through the first door, the next character could be a boy or a girl. They come into the second one, could be a boy. Might as well keep it in the same order, doesn't really matter though. Could be a boy or a girl. Could be a boy or a girl. Could be a boy or a girl. Okay? And now we're able to see all of the different paths and we can write out our sample space. So we could have door 1 with a boy, door 1 with a girl, door 2 with a boy, door 2 with a girl coming after, door 3, boy, right? Follow the paths. Door 3, girl, door 4, boy, door 4, the girl after, door 5, boy, door 5, girl. So sometimes it gets a bit repetitive writing it all out, but it is useful to have this written out sample space here. Okay, and now we can answer the question of what is P boy, comma, center stage door. So what is the probability, that's what the big P means, remember, of boy happening and center stage door. So how many combinations are boy and center stage? Well, we should have numbered these, I guess. 1, 2, 3, 4, 5. So our center stage door right here is number 3. So what is the probability of getting boy and door 3? Well, boy and 3, there's only one outcome. So that is our one outcome, one favorable outcome. How many total outcomes were there? Well, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes, including our favorable one. So there's a 1 out of 10 chance, which is the same as 0.1, which is the same as a 10%. We multiply our decimal by 100 to get a percent. It's a 10% chance that would happen. So showing it as a fraction and as a percent. Okay, so fairly straightforward. Just so you know, we could have also gone boy, girl, and switch the order since they're independent. The one following doesn't matter which order they come in. Could have been boy then girl, and then 1, 2, 3, 4, 5, and 1, 2, 3, given us actually the same sample space. Sometimes that's even a bit easier to do the least number first in the first part of the tree. But either way, it doesn't matter. Okay, let's look at another example. So a four-sided die right here is labeled 1, 2, 3, 4, and the spinner is divided into 5 equal sections here: fly, swim, glide, walk, hop. I'll just use the first letter of each. So it says create a table to show all the possible outcomes when the die is rolled and the spinner is spun. Okay, so for the table, you have one of each of the events on each side of the table. So let's have the spinner up top here. And the possible spinner outcomes are fly, swim, glide, walk, and hop. Okay, so we'll just make a thick line here to separate those. Okay, and those are all our possible outcomes for the spinner. And then our other side of our table, we have our die, which is our four-sided die, and there's only outcomes of 1, 2, 3, and 4. Okay, so now when I make these lines separating these outcomes as well, I get all of these sections. Okay, and I can, if you wanted to make it neat, you could sort of erase the ends of it. And so now I can fill this in and see where they combine. So in this box right here, that is where 1 gets rolling a 1 and spinning fly. You can roll 1 and spin swim, roll 1 and glide, roll 1 and walk, roll 1 and hop. Or you could roll a 2 and fly, roll a 2 and swim, roll a 2 and glide, roll a 2 and walk, roll a 2 and hop is H. Okay, or a 3, you could roll a 3 and then spin all of these different options. Okay, and so this is a really nice way when you have 2 events happening. A table is a really nice way to see the whole sample space. So you could have a 4 and fly, 4 and swim, 4 and glide, 4 and walk, 4 and hop. Okay. And here we see all of our possible outcomes. So one question is, in B here, is what is the P of 3, swim? So the probability of getting a 3 and swim. So we look through, where do we see a 3? Well, we're going to see a 3 in this row coming across. And there's only one 3 with an S for swim, and that's right here. So for B, the probability of getting a 3 in swim, there's only one favorable outcome. Well, how many total outcomes are there? Well, in each, there's 1, 2, I mean, you can count them, but there's also 5 spinner options. There's 4 die options, so we're counting by 5s, 5, 10, 15, 20 different possible outcomes. So it'd be a 1 out of 20 is the probability of getting a 3 and swim. And what about what is the probability of an odd number and hop? So in this case, there's going to be more than one possible outcome. Let's make this blue. So an odd number with hop. So we can find hop and all the odd numbers with it. So that's 1 and H and 3 and H. So an odd number with hop, there's only 2 possible outcomes. So that would be 2 out of 20, which could be simplified because those can both be divided by 2 to 1 out of 10. So there's a 1 out of 10 chance of getting an odd number with hop. Okay, and there we have it. Okay, so just key ideas of that section 5.3. You can use a tree diagram, a table or other organizer to help determine the probabilities. So you count the favorable outcomes, divide by the total number of outcomes to find the probability. Okay, so something we've already been doing. So here's what the tree diagram looks like. Here is a table, a nice neat table. And here they did sort of another type of organizer, I don't know, like a web organizer of the possible probabilities or of the possible outcomes. So that works too. Okay, so moving on, 5.4, application of independent events. This is actually very similar to 5.3, just getting a little bit more complicated in what they're asking. So just going to do one example from here. So a card is chosen at random. Okay, so we have these cards here. So 1, 2, 3, 4, 5 cards, and a die labeled 1 to 6 is rolled. So organize the outcomes in a table. Okay, so I would say for second 5.4, when there's only 2 events, tables are going to be the better organizer to use over the tree diagram. Tree diagrams can sometimes be quicker to find a certain outcome, but when you're looking at lots of outcomes, the tables are nice and organized, and you can sort of find some patterns and stuff. So let's make it organize all the outcomes in the table. So let's do our die on top. So for the die, we have 1, 2, 3, 4, 5, 6. And then for the cards, we have 6, 7, 8, 9, 10. 6, 7, 8, 9, extend it a little bit, 10. Okay, so it takes a little bit of time to make these tables. You just actually got to do the work for it sometimes. I know some of you want to just try to do it in your head, but it's a much better idea to actually just put in the work, make the table. Okay, and I'm just going to make these lines just a little bit thicker to separate my outcomes from my 2 different events. There. Okay. Now let's fill this in. So you could get a 6 and a 1. And again, it doesn't really matter what order you put these in. I'm just doing the ones that are going up and down first. You get a 6 and a 2, 6 and a 3, 6 and a 4, 6 and a 5, 6 and a 6. You get 7 and 1, 7 and 2, 7 and 3, 7 and 4, 7 and 5, 7 and 6, 8 and 1, 8 and 2, 8 and 3, 8 and 4. Okay, and so you just keep writing. I know it takes a while, but and right now some of these you may think you can do in your head, and you may be able to, but there will eventually be problems that are hard enough that you will just need to write this out. So just getting used to that. We'll be doing problems in grade 8 where you will definitely need to write it out to be able to see all the possible outcomes and find all the favorable ones. It's not always super easy. Okay, 10 and 6. So now we can go through the rest of these questions, find probability. So B, what is the probability of getting only 1 6? So the probability of 1 6. So this isn't the probability of, so 2 6s can't be in here because it's only 1 6. So how many outcomes is there only 1 6 for? So actually I'm going to say B, I'm going to just color in blue just to make it color coded. So I'm just going to tap beside all the ones that have 1 6. So this has 1 6, 1 6, 1 6, 1 6, 1 6. Well, the 6 and the 6 has 2 6s, so that doesn't count. But then all of these ones coming down here just have 1 6. And so I have 1, 2, 3, 4, 5, 6, 7, 8, 9 favorable outcomes here. So 9 out of, well, how many total outcomes are there? Well, counting by 6s, 6, 12, 18, 24, 30. Okay, 6 times 5 is 30. So there's 30 possible outcomes, so 9 out of 30. These can both be divided by 3. I can see that. and 9 divided by 3 is 3, 30 divided by 3 is 10. So 3 out of 10 chance of getting only 1 6. Okay, so what about C? What is the probability of getting at least 1 6? So you see, you have to be pretty careful. This here was only 1 6. This is the probability of at least. So you can have more than 1 6. At least 1 6. And in this case now, having at least 1 6 means you can have that one and this one and this one, because 1 6 is favorable. But you can also have more than 1 6, so the 6 and the 6 count as well. And all of these ones coming down here. There's no other outcomes that have a 6 in it. And so now there is 10. There's 10 out of 30. Okay, so 10 out of 30, which can both be divided by 10 to get a 1 out of 3 chance. Okay, let's find another color. What is the probability of the two numbers having a sum of 10? Okay, so for D, we are looking at probability sum of 10. So how many of these add up to 10? So what numbers add up to 10? Well, 6 plus 4 adds up to 10. 5 plus 5 does, but there's no 5 in our card numbers. So 6 plus 4 adds up to 10. I know 7 plus 3 adds up to 10. I know 8 plus 2 adds up to 10. And I know 9 plus 1. And look, we had this nice little angle line, straight line going across, and that's what you're going to see when you have these tables. You're going to see these patterns, especially when you're looking for sums and differences and things like that. Okay, so is there any other possible outcomes on here? Well, if we move to the left of any of these outcomes, so here's 6 and 4, well, to the left is 6 plus 3, which is 9, to the right is 6 plus 5, which is 11. Same thing here. If I move to the left of 7 plus 3, 7 plus 2 is 9, 7 plus 4 is 11. And so no, there can't be any other possible outcomes, because they're either going to be less or greater on either side of each of these outcomes. And so those are our 4 outcomes. So there's 4 out of 30. These can both be divided by 2. 4 can be divided by 2 to get 2, and 30 can be divided by 2 to get 15. So remember, when simplifying, you have to be able to divide both of them by the same number to simplify. Okay, and so E, lastly, is what is the probability of two numbers having a sum of 10 or more? So sum of 10 or more. So English is important here, because the sum of 10 or more means that the sum of 10 is favorable. So all these ones that we looked at before, this one, this one, this one, this one, those are all favorable, but also anything more than that, which is going to mean anything to the right of each of these on the horizontal line. So this one and this one would add up to more than 10. These ones would add up to more than 10. All these ones. These ones. And then, of course, the row that has 10, all of those are going to add up to 10 or more. Okay? And so now I can count all of these favorable outcomes. I have the green dot beside them. I could also just count how many don't have it, because that is shorter. 1, 2, 3, 4, 5, 6 outcomes don't have a green dot. There's 30 outcomes total. So if I take away those 6 that don't have it, that means there must be 24 out of the 30 outcomes that do have it. So now each of these could be, well, it could be divided by 2, and I'd get 12 out of 15. But you should also be able to see that 12 and 15 can each be divided by 3, to get 4 out of 5. So there's a 4 out of 5 chance that the outcome will have a sum of 10 or more. Okay, so you can see it was very useful to have this table written out for finding some of these more difficult probabilities, or the number of outcomes. Okay, so hopefully that makes sense. Sorry, I got a little bit messy there. Just watch it again if you are a bit confused. Okay, and the last section is just quickly on conducting probability experiments. Okay, so, and this is really, we're just looking at, okay, so we know that the probability, the possible outcomes of flipping a coin are getting a heads or a tails, right? But does that mean that you're always, since there's only two outcomes, there's a 50-50 chance, does that mean if you flip a coin 10 times, you are for sure going to get only 5 heads and 5 tails? Well, no, we know that if you were to take a coin, you might get more than 5 heads or less, and it doesn't always come out exactly that way. So when we do these probability experiments in real life, instead of just looking at the theoretical possible outcomes, when we actually do them, we get slightly different results. And so we have these two things called experimental probability and theoretical probability. Okay, and we'll talk briefly at the end about how you can get those two things closer together. So at summer camp, the counselors have created an obstacle course. So each camper must travel through the obstacle course one at a time. So halfway through the course is a fork in the path. So the fork in the path means they have two options. Campers must choose to go left or right. Okay, so the first option to go left or right. Halfway along each fork is another fork, so a second option. Campers must again choose to go either left or right. Okay, so as they're going through, no matter what path they take, they're going to have two options of left or right before them. Andrew flips a coin, hey, that's my name, twice to model the possible choices of any camper. Okay, so just like left or right, two possible outcomes, a coin, heads or tails, two possible outcomes. And so you can model their choices if their choices were random by flipping a coin. So a head indicates left and tail indicates right. The following chart shows the results for 100 pairs of coin flips. Okay, so he has this table here, and so he would flip a coin twice, and then heads always meant left, and so he wrote down the results. So in the possible outcomes, we're getting, now you could make your tree diagram here too. You could get a heads or a tails, and then you could again get a heads or a tails off of each of those, heads or tails, and so we see the 4 possible outcomes: heads, 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 tails, tails, heads, tails, tails. Okay, and those are the 4 possible outcomes he has in his chart. So heads, heads means 2 left. When he flipped the coin, 100 pairs of flips. He had 22 pairs of flips that were heads and heads, 24 pairs of flips that were heads and tails, 27 pairs that were tails and heads, and 27 pairs that were tails and tails. Okay, and so if this was theoretical, if it was totally split evenly, you would expect 25 from each. But in experiments, it doesn't always work out exactly that way. It's close, but it's not exact. So from the data, what is the experimental probability of taking 2 left turns? Well, there's 22 of the favorable outcomes, 22 heads and heads. So this would be 22 out of the 100 total pairs of flips. Okay, so 22 out of 100. Well, what is the theoretical probability of taking 2 left turns? Well, if here's our 4 outcomes, heads and heads, heads and tails, tails and heads, tails and tails, there's only one outcome, heads and heads, that is favorable, which is 1 out of 4. So that is your theoretical probability. Okay, now these may look different. 1 out of 4. And so C asks, compare the experimental probability with theoretical probability. Well, which one of these is greater? Well, when you just look at them right now, you see the 22, and 22 seems much greater than 1. But to really be able to compare fractions, they have to be with the same denominator. So we could take our 1 out of 4 and we could multiply it by 25, and therefore also multiply the top by 25 to get an equivalent fraction of 25 out of 100. And now that they both have a denominator out of 100. So 1 out of 4 is same out of as 25 out of 100. They have the same denominator. We can compare them, and we can see, okay, the theoretical probability is greater when we're comparing them. Okay. And that's all you need to say when you're comparing them. Just say which one's greater. And you could say whether just by a little bit or by a lot. In this case, it's not by too much. Okay, so there's our experimental probability, where you actually have results of these probability experiments, doing it a bunch of times. And we have our theoretical probability, which we find using our tree diagrams or our tables. Okay. So the probability of an event determined from experimental outcomes is called experimental probability. So 2 different types of probability we're looking at here. Experimental outcomes are usually collected in a tally chart and counted at the end of the experiment. So like here, shows, they have this tally chart of how many times they got each one. I don't know why this says 2 when there's only 1 tick here, but there's probably supposed to be another tick. The probability of an event determined from a list of all possible outcomes is called theoretical probability. So that's what we've mostly been doing, finding probability from our list or from our tree diagrams and such. And experimental probability and theoretical probability are not always the same. So they're not always going to be exactly the same, but you should be able to get them close. And you can only get them close if you do a whole bunch of the experiment. So you do a whole bunch of trials. So if you're flipping a coin, you could flip a coin twice and get heads both times. That would make it seem like there's a 100% chance, according to your 2-flip experiment, there's a 100% chance that you'll get a head. But if you were to flip that coin 1,000,000 times, it should come out pretty close to 500,000 for heads and 500,000 for tails. It may not be exact, but it will come a lot closer to 50-50 the more experiments or the more trials that you do. Okay, so that's how you can get your experimental and your theoretical closer. It's just by doing the experiment more, if the theoretical probability is correct. Okay, so sorry that was sort of long. We went through 3 sections. Let me know if you have any questions. Really, we're looking at a really important thing is being able to make these tables, make the tree diagrams, and be able to read all of the possible outcomes to find your probabilities. Okay, so doing a question like this one here, this is really the main focus. Okay, let me know if you have any questions. Good luck, grade 7s.